Is it possible to parallel up power transistors like this so that you can get increased load current? Some sources say yes, some sources say no. I'm Professor Fiore, and I'll explain it all to you right now. Hello, folks. So the question today is, can we put power transistors in parallel for something like a Class B amplifier in order to increase the output current? I have seen texts that say you can't do this. On the other hand, I've seen actual commercial amplifiers that do that quite successfully. Well, the quick answer here is yes, you can do it, but the reality is there's a catch. There's a gotcha. I'm going to explain the whole thing to you. So here's, in a nutshell, the issue. If you could find a power transistor that met all of your specifications for maximum current, maximum voltage, maximum power, this would not even be an issue. In other words, you would just use the specified transistors and be done with it. However, when you're looking at very high powers, it might not be possible to find a transistor that can meet all three of those qualifications. In other words, it might meet the current, it might meet the voltage, but you can't get both of them. Okay? So an obvious idea is we'll take 2 or maybe 3 transistors, put them in parallel so that they will share the current equally among them. So if I have 2 transistors, the idea is each of them will handle half the load current. 3 transistors, each of them will handle 1/3 of the load current. Simple idea, right? Well, the problem is bipolar junction transistors have a positive temperature coefficient of transconductance. Now, what that means is that when they heat up, they would like to draw more current. That's a serious, serious problem, because any 2 random transistors that you would throw in there, right, from a manufacturing batch, same model number, same make, right, they're still going to have slight variations in parameter. Now, what that means is the currents are not going to be perfectly matched when you set them up. The end result will be one of them is going to carry a little bit more current than the other one. You know, maybe it's only 52%, 48% for a pair, but it is a difference. And ultimately what will happen is, as these things are conducting, that one with 52% is going to get just a little bit hotter than the other one that only has 48% of the total current. Now, because it gets a little hotter, it conducts more. And because it conducts more, it gets hotter. And because it gets hotter, it conducts more. And what ends up happening is this spirals out of control. In other words, we have a positive feedback loop on temperature. This keeps on going until the point where, you know, it's no longer 52-48. Pretty soon it's going to be 70-30. You know, maybe it'll hit 90-10. Who knows? The thing is, ultimately, that one transistor that's taking the lion's share is going to blow up. It's going to meet and eventually exceed its power handling capability. And the sad thing is, when it blows up, if it blows up as an open, all you're going to have left is the other transistor. And guess what? That one's going to die in short order as well. All right? So it's sort of a murder-suicide pact in a way. All right? So we have to do something. There's something we have to come up with to compensate for this positive feedback effect. We need some kind of negative feedback in order to fight the positive thermal feedback. It turns out that that's relatively easy to do, although it is not imperfect. But before I go any further, I do want to bring up the fact that you can find devices that have a negative temperature coefficient of transconductance. Power FETs, power MOSFETs are like that. So you can put those in parallel with much less difficulty. You don't really have this problem. But bipolar junction transistors, this is an issue. And we give it the rather prosaic name of current hogging, right? One of the transistors hogs all the current, right? It would be kind of like if you went to, an all-you-could-eat buffet, and the more you ate, the hungrier you got. I mean, that would be insane, right? Pretty soon, you'd be Mr. Creosote in a Monty Python routine, Anyway, let's take a look at what's really going on here and a little bit of a gotcha when it comes to using a simulator like this, right? So here we are in Tina TI, and I'm making a very sort of basic Class B amplifier, and all I've done is just cloned the output stage with another pair of transistors, right? So I've got 5-volt power supplies on here, and I'm throwing in a 4-volt peak input. We would expect there to be a 4-volt output. With this configuration, however, half of the load current is going to go through the T1, T3 side, depending on the polarity, and the other half of the load current is going to go T2, T4. All right. First, let's just do a transient analysis to make sure that this thing even works. All right, so that's a 1 kilohertz signal, so I'm going to go from 0 to 2 milliseconds. We can see a couple cycles of this. All righty. Open this up, and we'll get our little legend here. So we can see, all right, the dark blue here is the generator. There's the 4-volt peak. V load is a little bit less than that, not much, and we do expect, because it is after all a follower, we don't expect a gain of exactly 1. We do expect it to be in phase, and we are in fact losing a little bit, right? We have just about 3.8 volts here. So instead of 4 volts peak, so we're losing, a few percentage points, not too bad. The green down here happens to be the currents, right? The IC1, IC2 measurements over here. If you want to, we can separate these out and see exactly what's going on, right? So there's the 2 current pulses, and they look identical, right? I mean, they're peaking up just below 20 milliamps apiece. So yeah, it looks like these things are, combined the way they should be, all right? But that's kind of a gotcha. What do I mean by that? Here, I'll show you what I mean by that. I'm going to come into DC and do a quick nodal calculation. So here are the DC currents that we're getting for the two, right? Roughly 2.25, right? Roughly 2.25 milliamps DC for each of these. And then if we look at the AC, do the same thing for the AC. Right, we're getting like 6.66, ooh, devil, 6.66 milliamps RMS for each. And they're perfectly aligned, right? I mean, this is out to 5 digits. Well, guess what? In the real world, you're never going to get that kind of matching. You're going to have to do some kind of parameter swap over here, okay, to see what's going to happen in the real world. I mean, in the simulator, everything is perfectly matched. In the real world, they're not. So what you could do, right, to kind of get an idea of the sort of mismatches, you could go in and do some measurements on your transistors, and then you could come in and monkey with the various parameters here, right? So this says, for example, for the 3904, it says the forward early voltage is 40 volts. Okay, so you might go out and measure it and find out, well, I got one that's 35. All right, there's different parameters here that you can sort of monkey around with. You can change, the reverse saturation current, whatever the heck it is, right? And you can get a better idea of what the matchup here is going to be. You would like the matching to be as close as possible. You would like this ideal case where the parameters are identical. But that's not reality, and you have to deal with reality. So what I'm going to do is, instead of monkeying with all of these individual ones, I'm just going to put a different transistor in here. Something that's sort of in the ballpark, right? Not like totally crazy. But, I've got 3904 and 3906 transistors in here, primarily so that you can, monkey with this in your own lab. It's a small signal, right? I mean, this is not a power amplifier. It's configured as a Class B power amplifier, but, these are small signal transistors, right? So I'm going to put another common small signal transistor in here, a 2N2222. All right, so we'll just say OK on that. Now I want to repeat that what do we get? Remember, we had 2 1/4 mils and 6 2/3 mils for AC. So let's go in, we'll do the same thing and see how far apart these things are now. All right, so for DC, well, now I'm getting 2 mils and 3 mils, right, instead of 2 1/4 each. All right, that's worth remembering. I mean, this thing is, you know, like 50% larger, okay? That's a pretty good mismatch. I mean, that's what we're trying to see is the mismatch. Go in and look at the AC. And remember, last time we had like 6 2/3, so this one's a little low. Now it's 5.3 mils. This one's 9 1/4, basically. So this is actually drawing most of the, you know, the majority of the AC current. So this is really illustrating the problem that I'm talking about. This is the AC current, right? The RMS current. This thing is drawing considerably more than transistor number 1. Okay, so how do we get around this? Other than maybe trying to go in here and, you know, digging through piles of transistors and trying to match them up. You'd rather not do that. You know, if there's first of all, there's the expense of doing it, right? You know, that's a rather laborious process. The other thing is, if something goes wrong, you need to repair something. You know, if one of these transistors fails for some reason, you got to go out and rematch everything. You know, that's a total pain, not very practical. You don't want to have to do that. So, you know, what are our options, right? Where can we go with this? Well, there's a fairly simple solution, and that is to, you know, again, we want to do like a negative feedback thing. Think negative feedback, negative feedback. Well, we can go something like this, a little bit of a modification to this circuit. And what I've done is I've thrown in some little 5 ohm emitter resistors, right? Now, normally we would refer to these as like swapping resistors. You know, if this was a little class A, you know, common emitter kind of amplifier, right? We don't normally put swapping resistors in a class B amplifier. But here's the way this works, right? Now follow me on this. So ideally, we've got a drop across D1, you know, approximately 0.7 volts. And without these little resistors, that's what you would see across this base emitter and what you would see across this base emitter, because they're essentially in parallel, right? But these two devices are not perfectly matched. In other words, their transconductance curves, their VBE curves versus IC are not identical. So for the same voltage, we get slightly different currents, right? In our case, you know, what we saw was like for DC, 2 milliamps and 3 milliamps. And for AC, we saw like 5.3 and like 9 1/4 or something like that, right? There was, you know, pretty sizable differences with these two transistors, with the 04 and the 22. Well, here's what happens, right? This transistor has a higher current. So what happens is we get a larger voltage across R6 than we do across R4. Now, because that's essentially in parallel with the T1 R4 combo, if the drop across R6 is a little bit bigger, that forces the drop across the base emitter of transistor 2 to be a little bit smaller. And if that drop is a little bit smaller, that means the associated current must be a little bit smaller. So when one of these transistors starts conducting more, the associated emitter resistor produces a larger voltage, and that's like turning down the volume, so to speak. There's less voltage left for the base emitter, so that brings down that current. All right? So in this case, you know, I've chosen a fairly small value, 5 ohms, and that's small compared to the load. I'll get into that in just a second. Like, you know, what kind of numbers are you going to want to throw in here, right? Let's go in and do the little DC and AC current analysis and see what we come up. All right, so now I've got 1.6 mils in the 04, and I've got roughly 2.1 mils in the 22. And remember, when we did this in the first circuit, right? Not the very first circuit where it was 2 1/4 each. When we did this in the one with the 04 and the 22, this current, right, came up to be about 2 mils, and this current came up to be about 3 mils. All right, they're both lower, which shouldn't be a surprise, because there's really less voltage for each of the VBEs, so they should both fall down a little bit. But I'm more interested in the ratio, right? It was a 2 to 3 ratio before. Well, it's not a 2 to 3 ratio. It's less than a 2 to 3 ratio now. If it was a 2 to 3 ratio, with 1.6, this would be around 2.4. So we've managed to rein that in a little bit, at least for the DC. Let's see what happens with the AC. Okay, so I got 5.8 for the AC current here and 8 mils for the AC current over here. And again, in the original circuit without the emitter resistors, right, instead of 5.8, we were looking at like, I think it was 5.3, okay? And then we were looking at like 9.25 for this. All right, so this is a little higher and this is a little lower. Great. I mean, it'd be fantastic if they were identical, but we've really managed to rein that in. But again, I want to stress that I'm not talking about the slight variations between two same make and model number transistors. I've thrown in a completely different kind of transistor, right? I mean, I don't expect these things to be super, super tight. And I'm doing this on purpose, right, to sort of magnify what the issue here is. All right, now, if you put in a larger resistor, right, these 4 resistors are bigger compared to the size of our load, you can get these things to rein in a little bit more. In other words, get them closer and closer and closer. But there is a point of diminishing returns. You are going to lose a little bit of signal, all right? And it's worth asking, well, okay, what do I actually get out of this thing? I mean, do I have a halfway decent looking output? So, we can do another transient analysis. Remember, last time we got it was somewhere around, I think it was about 3.7 and change volts peak. All right, so let's see what we get now. I mean, we are clearly getting a nice sine wave. And it's okay, that's just 3.7 instead of, like I said, I think it was 3.7 and change, close to 3.8. So we've lost a little bit of signal. And as I said, if you crank these up, if you put 10 ohms in here, 15 ohms, 20 ohms in here, the larger and larger that is, the less and less signal you're going to get to the load because there's a little bit of a voltage divider effect going on here. All right, so you don't want to get too large with this because you're going to start losing power. Right? The point is not to heat up these things, it's to deliver power to the load. Okay? There is one more thing I want to throw in here. And that is, if you've seen some of the other videos on the Class B amplifier, you know that there is a little technique for an automatic current limiter, an overcurrent limiter, where we place a little bypass transistor across a little resistor like this, right? And when the voltage gets too high, it turns on the transistor, it bypasses the power transistor, and it produces a current limit, which is a little bit nicer than using a fuse, right? Fuse blows, you got to replace it. This, the short, for example, on the output goes away, it automatically resets itself. So it's much nicer. So you can actually do double duty with these things, right? You can put those little sort of protection bypass transistors across here, and that way get, like I said, 2 functions. You get the current limit and you can do this current sharing thing. All right? So if these aren't large enough, you're going to wind up with a little bit of a thermal runaway, the thing that you're trying to avoid, although it won't be as obvious, it won't be as nasty as if you didn't have them in here at all. So there is kind of the sweet spot, and that's something you're going to have to play with a little bit. But when you look at power amplifier schematics, you see these little resistors, that's what they're doing, all right? Like I said, you might see the little secondary transistors out here, the current protection transistors, but that's what you're going to see. When you go back to like the 1970s, for example, back in the dark ages, when people were first making large audio power amplifiers, we had concert PA systems, and we needed really beefy power amplifiers. So, I think back to the days of, the old Crown, what was it, the DC 150, I think, the phase linear 400. These were sort of classic 1970s power amplifiers, pumping out a couple hundred watts in the case of the phase linear, per channel into 8 ohms. The Series 2 came out, and they had a bigger version of that. You're getting like 300 watts per channel. Well, okay, you had to find transistors that could do that. There weren't individual power transistors that had the sort of specs that you needed. So I think it was in the Series 2, they had 3 power transistors in parallel. And you would see these little, like I said, feedback resistors out here. And, you know, they work great. I mean, I used some phase linear Series 2 power amplifiers for quite a few years. You know, other amplifiers as well. I'm not trying to shill for phase linear over here, but that was a common design. Yet, on the other hand, I have, as a professor, reviewed textbooks. You know, way back when, before I wrote my own textbooks, right? You know, I would look through and see, you know, who's got what. Let me look through their textbook. And I reviewed textbooks that literally said, you can't do this. You cannot take transistors and put them in parallel. But really, you know, to be fair, what they were really talking about was this. You're asking for trouble if you do this, right? You have to have some kind of feedback in here. If you just do this simplified kind of thing, it's going to heat up, and yeah, they are going to blow up, right? You know, unless you're very, very careful about not pushing them. But then, you know, what's the point in that case, right? The whole point of the power amplifier is to produce some power, all right? So here we are. You can set this up, like I said, in a lab situation. You wouldn't have to get 2222 over here. You know, just a handful of 04s and 06s, you'd be able to, you know, put a couple of ammeters out here, and you'd be able to see what the differences are. And then you could flip over to this configuration, and you'll be able to see yourself, yeah, these currents are going to line in. They're going to be closer, right, to each other, and that's the trick. They're going to be closer to each other than if you didn't have them in there. Or if you have a resistor substitution box or a small, you know, potentiometer, you can just sort of like crank these things up, right? Pot's a little trickier because you want to get these things to, you know, track. You don't want like 5 ohms here and 7 ohms there. But, you know, a resistor substitution box could work. Or just, you know, pop in some resistors, whatever. But, you know, like I said, you could hook this easily enough on a proto board and see for yourself. And that's always, you know, a great thing. I love simulators. You can play with them, you know, do these little what-if kinds of investigations very quickly. But, you know, there's something about actually building up a circuit, going in there with a meter, and, you know, futzing with the values and the components and seeing what really happens. To really drive home what the relationships between the components and the circuitry happen to be. All right. Well, I hope you found this one entertaining and enlightening. And I'll see you next time. Take care.